Hello, I'm Troy Hofstrand, graduate student at St. Louis University, and this is for Introduction to Machine Learning. My project for this final presentation has been about authenticating banknotes or checks with machine learning algorithms. And I also threw in a couple voting ensemble techniques. So just a quick overview of the problem that I was looking to solve, or found a data set that would allow me to solve. One of the big issues in especially in areas like Bangladesh, they're having a large problem with fraudulent banknotes or fraudulent checks, counterfeit checks. And it seems to be a pretty major issue, as it's easier nowadays to forge a bill, as you can just scan and print something. Back in the day, you'd have to hire an artist and a whole team, but this has become more commonplace, as you're commonly seeing counterfeit checks, and often it can be a pain to authenticate. Um, but one of the ways that scientists believe would help streamline this process would be through technology, of course. So what is the problems exactly with counterfeit checks? Well, you think, oh, it'd just be a problem for the bank, but it actually can contribute to disrupting a whole economy. It can mess with the financial state of a lot of large businesses. If banks go under, it's a big issue. So hopefully this problem could be solved. It could also counterfeit bills and take money from people. It would be a whole mess. So trying to help eliminate this issue. And the way I have presented and I have set up the solution to this problem is the first thing I did was I found the data set of the UCI machine learning repository on banknotes, and they have a data set with um, 5 features. They are skewness, kurtosis, variance, and entropy. And the 5th one is class. So the target feature we're looking for is class. For class, a 1 is a fraudulent bill, and a 0 is an authentic banknote. All the other ones, it seemed like I would be doing some sort of image scanning, image processing, like image learning algorithms here or technology, but actually the data itself was transformed from image data using a wavelet transform tool. So it is actually numerical data that we'll be working with. So the next step after inputting the data and working with it, I have examined it. There's only about 1,600 entries in this data set, which is relatively small. So after doing data cleaning and some pre-processing, I determined that because the data set's so small, even though there was correlation, which I will actually show you right now, even though there was minimal correlation, as you can see in this matrix here, there seems to be a correlation, and it looks like it might be an issue, but with the data set being so small, I just determined that because I don't want to already reduce the small size, it would be unnecessary to reduce any redundancies, because if I cut down the size anymore, the training test split's not going to work out as well. And the next thing, I was exploring the data, and one of the interesting things I found using this scatter plot here was that for the fraudulent bills 1 and the authentic bills 0, the variance overall actually tends to be lower. So we're already seeing a little bit of a pattern here. Grouping of higher variance usually means probably an authentic banknote that you're looking at. And then the next step was to create my train test split. The split I decided on was 70-30 because 2080 barely left any room for the testing size. It was just too small. And it seemed to skew a lot of the algorithms I did in the results phase. Because the data set was so small, they performed almost too well. So I tried the 70-30, and it seemed to be a lot more reasonable of a result while I was testing. So then after I did my train test split, I did my model creation. And for the model creation, just fit whatever machine learning algorithms just came to mind. I just picked, I think, 5. Um, we got logistic regression, naive Bayes, support vector machines, use random forest, KNN, and then I even have my own neural network just as an attempt, as a little experiment for myself, see if I can do it. And then we use the sklearn metrics to do a metrics analysis. We took in the accuracy, the precision, the recall, the AUC value, and the F1 score, excuse me. And as you'll see here, this was the results. Maybe I can zoom in a little bit. Or not, that didn't work. This is the results of just the initial testing. And as you can see, K nearest neighbors, 100% every category, which I thought was absolutely outlandish. When I first did this, I was baffled and I thought maybe I'd done something incorrect. But then I referred back to a research paper I've been reading. They studied the same topic. I can show that here as well. They had similar, very high results for KNN and for almost all of them, actually. Nothing below 70. Oh wait, oh I see one below 70. Nothing that low. And I actually had very similar results, and I was very pleased to see that I wasn't alone in this. Naive Bayes tended to do worse for them, as it also did for me. And KNN tended to do especially well. The reason for that could be a small data set, but also, like I said, as you can see, these groupings I think are really they lend themselves well to KNN because of how close they are. Be easy just to group them all together. And then the next phase, I decided to do a hyperparameter tuning and a cross validation. Just the same thing I just did, just changing up a little bit. I used randomized search. It's a lot like what was in the final exam for this course. I used the same models again. Even changed up the neural network as an attempt, see if I can get anything good out of that. We're going through the same exact metric standard here, except this time we're using our search values. So see if we get something different. And as you can see here, the KNN did not do as well as last time. Very well, but not all 100% like last time. Support vector machine actually took the place as the number 1 here. It turns out, I guess, the K nearest neighbors does not need any hyperparameter tuning. I really probably shouldn't have when it was already 100% for each score, but I decided better safe than sorry. Might as well try, see what happens. Once again, I do think this data set, if it were bigger, we would not see 100% at all. But with the size where we have to work with, this is what we're going to get. And even those people that did have larger data sets had something similar. As you can see, they use support vector machines as well. If I can find it. Passed it. Oh, they did not, but theirs would also have scored pretty well, I'm sure. The Bayes model, again, even after hyperparameter tuning, does not seem to work as well. And then the next step, I decided, actually, professor told me to take it up a notch. How about we try a combination of machine learning algorithms? So next phase, I used the voting ensemble method, which essentially allows the combination and the collaboration of multiple machine learning algorithms. So a couple of these I just chose to see what would work best. I'm not saying I went too deep into how I chose. I just wanted to see what I could come up with and what I could get. And I tested a couple, and these were the 3 that I kept for the final results. I have the combination of naive Bayes with KNN. I was hoping to put the worst with the best, see what would happen. The next one, I did logistic regression in KNN again, because KNN performed so well. I think maybe it could boost these other ones that performed all right. And the final one, I actually chose to use 3 machine learning algorithms. I used logistic regression, random forest, and K nearest neighbors. Now I'll show you the metrics we did, something very similar. This time we're only going for accuracy. So I'll show you right now what we got. And for the naive Bayes with KNN, we got a 90, not very good, better for naive Bayes, but not as good for KNN. Logistic regression plus KNN, we had 100%. It's not too surprising as logistic regression did around 98% total. So combination of KNN, it's no wonder it's 100%. And then with all three at the bottom there, logistic regression, random forest, and KNN, we have 99.5%, which is also phenomenal. And even more interestingly, the paper I was also just referencing earlier, they also used a voting ensemble algorithm, which I can show you their results in combination with mine. Their NB plus KNN, 99%. Theirs performed better than mine. Not quite sure why that is, but theirs did relatively better. They also did LR plus KNN. They got 100% across the board, no surprise. I was very similar to that. That score was almost the exact same. I don't believe they did any 3-part testing, but it was very similar. I was very pleased yet again to get something something similar with other scientists out there. So that's the results portion of this. What do I think about these results? Well, I think it's looking pretty promising for machine learning algorithms to be used for this kind of behavior, as it seems like this problem is the epitome of a machine learning classification problem, right? Real or not real? Is the check real or not? And we're using these still images of numerical image data. It's really something interesting. And I think this could be extremely helpful. I'm not sure if this is already implemented. I use in my own time, I use a electronic banking system on my phone, which actually allows me to scan checks via photos, and it actually reads the numbers. I'm sure something similar is in place there. I'm not sure quite what, but I would think that yeah, it can scan and tell me if the check is real or not, because sometimes I have to retake photos. So the real downside to this is it has to be a pretty high quality photo in order for this to work. I'm sure that'll be less of an issue later on, but I think authenticating banknotes with machine learning algorithms and voting ensemble methods is really something promising. And I think it's something that can really help countries out that are suffering financially from such fraudulent activity. I think that's about all I have. Thank you for watching. I hope you learned something. If you'd like to see my code or my paper, you can email me. I'll get it out to you. Thank you. Have a great rest of your year. See you next time.